for joining us. My name is Roger Sims. I've been with Fluke. Actually, it's a little outdated. I've been with Fluke for almost 15 years. I'm a senior calibration technician there, and I handle all the system calibrations and do some other various calibration, specialty calibrations throughout the lab. All right, today the agenda is system calibrations. We want to look at system calibration definition, guidelines for choosing reference equipment, and then going through the actual system calibration process. Okay, what's system calibration? It's calibration where the readout and the probe are connected as normally used. Okay, so plug together and it reads temperature. When you put the probe somewhere warm, it gets warmer. So our thermometer is used to verify the nominal temperatures. Okay, do that for obvious reasons. You need to have that as a standard. For accredited calibration, the thermometer is also used as a transfer standard, and that will aid in your traceability purpose. A report of calibration summarizes the received condition or as found state and any changes to the system that are made. A completed condition or as left state, and then also a documentation of traceability. The nominal temperatures are used for both as found and as left data. Right. There are two types of system calibrations. One, system verification calibration, and there's a true system calibration, or loop calibration, as it's sometimes called. System verification calibration consists of verifying two individual units that have individual calibrations. So the way we would do that is we would record as found data as a system, both units connected, and then the as found data is taken. We would separate the two units and send the probe off to be calibrated by itself, and the readout also calibrated by itself. Upon completion of the individual calibrations, the equipment turned back to my lab, and then I would take as left data on it. That should provide verification that yes, the probe calibration is valid, and so is readout validation or readout calibration. System calibration or loop calibration is what we're going to focus on today. What it consists of is, again, we will bring the units together, but making as found data. We will not separate the units. We at that point evaluate the data, determine if we need to run an annealing process, or if we can go ahead and align the data or align the units, and then take as left data. Okay. Something to note here. The system is calibrated, essentially married together or linked together, because when you're doing this type of a calibration, any errors that may be inherent in the readout will get focused into the data and the alignment of probe calibration coefficients. All right. So we need to have a couple of things ahead of time. We need to know what the range of our application is, what temperature range we need to run our calibration through. Some is typically out there. Have different ranges. Super freezers, cryo -95 to -60, freeze drying -80 to -80, blood banks from -50 up to -30 degrees, disinfectors around 70 degrees, autoclaves, food processing and process control instrumentation all above zero, and they can get quite high in temperature. All right. What you want to do is you want to try to link the best type of system, the best equipment for that type of a temperature range. Okay. For example, today we're going to be monitoring temperatures in stirred fluid or baths. We operate at a range between minus 200 degrees and 300 degrees Celsius. And what we wanted for our requirements, our tolerance needs to be or less than 7 millidegrees at 300 degrees maximum. So for that, we're looking at a system, a Pheno 2A or tweet at a 5615 probe, the 6-inch length, and it has a system accuracy of approximately 15 millidegrees at 0, and it will be well within our limits at the 300 degree maximum. Okay, so another thing we need to look at is the reference systems that you're using need to be at least 3 times better than the UUT system. So for this particular item at 0 degrees, we would like to have it at least 0.005 degrees, 5 milligrees. So what we're going to use is Fluke 1595A super thermometer, 5699 thermometer probe, which is a platinum resistance thermometer. The system would have a combined accuracy of, or a combined uncertainty of 5 milligrees. All right. So if we're looking at a temperature range between minus 200 and 300 degrees, if we go by ITS 90 points, 5 test points we would be looking at to cover would be minus 197, minus 40, or the freeze point of mercury, 0, which is the triple point of water, 2, which is the melt of tin, and 300 degrees, which is actually a non-TS 90 point, but we've that's quite handy to have, so we've developed that one through time. The ITS 90 subrange 8 will have the 232 and 300 degree test points, and the subrange 4 will include the minus 197 and 40 degree test points. So by the S90, we would use minus 189.344, which is the triple point of argon, or the boiling point of LN2 of liquid nitrogen is approximately minus 197 and is an acceptable substitute. Okay, everybody has a triple point of argon that they can actually use. They're rather expensive, and at this point it's still hard to come by. The point of mercury is minus 38.834. Triple point of water is 0.010. Tin is 231.928 degrees, and then the 300 degree is a custom point. So that happens to be the maximum limit of a cinch probe, just because when putting it at a higher temperature, you stand risk of overheating the transition handle. Right. The next thing we need to look at are heat sources. Okay, if you need extreme accuracy, fixed point cells are going to be the way to go, and that would actually require you to use a fixed point of argon, a fixed point of mercury. It would to use a fixed point of the RTPW, triple point of water, and then you'd still have to do a comparison at 300 degrees. Baths, you could well cover all of that except for the liquid nitrogen. We do have baths that reach down to minus 80 and all the way up to 500 degrees Celsius. Don't need quite as much accuracy, but trial wells are also a very good way to go. The only thing that they don't cover in that group would be the liquid nitrogen point. Okay, so I just went through that. What I'm going to use is for my equipment here is I'm going to use a 7196 liquid nitrogen doer. I'm going to use 7341 compact bath, 6331 compact bath. All of those are Fluke products, and they're very stable, so that's why we like to use them. And so mentioning that, the key is stability on all of this. Any stable uniform heat source will do. It has to be stable. All right, I'm going to explain a slide here for a second.
Yes, put together industrial temperature readout and probe selection guide, and really what it is, as there has been talking about, when you're doing a system calibration, it's important to know what are the correct combinations to use as far as a readout and probe. So that's the reason we put together this guide to give you a high-level reference of the different Fluke products, the readouts and the probes, and combining those together, what would be the total accuracy that you could see. So the reference is available on our website. If you're interested in that, just go to our website and you can download that reference.
All right, let's get into our process steps for doing system calibration. The thing we want to do is a reference thermometer check. Then we want to record the as found data, evaluate it. At that point, we determine the next step, whether we're going to anneal it, align it, or reject it. Anneal if required. We're going to new requires if the new coefficients if the data is good, and we'll program the new coefficients into the readout. Then record as left data. Then we'll evaluate those results versus the limits, and if we're ready, then we'll go ahead and we'll build a report of calibration. Now, this flow chart the whole process. So let's get into it. The first one is the reference check. Okay, it's very important. If you don't know where your reference equipment ends at the beginning of the calibration, do you know if it's deviated from the end? It's better to take an as-found reading. And in my lab, we can as-found reading, and then after we're done with the calibrations, before we start a new one, take another reference reading. So it's always good to know exactly how your references are performing. Here, you can see what I'm doing is I've got my my SBRT in a full-size RTW cell. It's in a 7302 maintenance bath. And I got a picture also of the 595A readout display. As you can see right now, I am reading 0.0101 degrees Celsius, and where we're wanting to be at 0.010. I think 1/1000th of a degree is probably acceptable. Right. The next step is we're going to record our as-found data. Okay. We always start with a 0 degree reading. Okay, and I'll explain this as we go on. But the 0 as found. Then we are the above 0 degree temperatures first. Take another 0 degree at midpoint, and then we take the below 0 temperatures, and finally we take another 0 as left point. The reason we take multiple 0 degree points is because we can watch the probe. It's changing through the different temperatures. If it is shifting, it is repeating the resistance very well, we may have a problem with the probe. And that's one thing that we'd like to use as a diagnostic tool as well. We skipped a couple of slides here. Let me go back. Okay, this is really wanted to make sure we had covered as well. Okay, data sheet that I have, it has spaces for the equipment used. It has spaces for the units under test or the devices under test, both models and serial numbers of everything. You need also make sure when you're doing a system calibration, you record the found coefficients from the readout in reference to the probe. So for this one, we actually have an RTPW reference value on the probe for the system, the DUT, of 9.9399 ohms at 0.010 degrees. Okay, that's what it's been programmed as. And you can see we have an A high and a B high and an A low and a B low. Those refer to the sub-ranges that we're using. An A4, B4 would be the low, and the A and B would be the high. Those are important. If you get those combinations mixed up, your system's not going to indicate correctly. Also, you need to have the reference temperatures that you are using down so that you have them recorded. You don't want to deviate from those. When you go to do your as left, if you use different reference points, the calibration is it's not the best calibration. Right, so moving back, where are we going? After we've collected all the as found data, and that includes reference temperature. Let me go slide again. It includes the actual ref temperature recorded by our 1595A and our reference SPRT. It covers the temperature that our DUT is reading and distance that your probe is reading through your DE readout. Okay. So record the max of both the temperature and the resistance in this case. Right. When we evaluate the data, what we're looking at is the error between the reference and the UT or UUT. And there are certain criteria that you want to look at. Right. You want to look again at the TPW values. You want to make sure they're following very close. You also are looking at the other temperature differences. If they're not bad, that's great. The concern is you want to have a stable RTPW that says, okay, our probe is very repeatable and get some good measurements out of it. There. All right. So is the good? Is we'll go through and send it into an alignment. If not, may elect to anneal it, and we'll send it through a second time. If it's really bad, if we have a probe that is intermittent overload or mass temperature, or whatever. If something that's obviously bad, we'll just send it out and reject it. Okay. So again, if the measurements between the 3 measurements are repeatable, if they are great, awesome. There should be minimal differences, specifically between the 0 mid and the 0 as left. The main reason is because when you're at the high temperatures, there is a slight possibility of a slight anneal. Okay. And that's why you're always looking at the mid as left. That's the small shift should happen, and that's where everything should run. Large of resistance can indicate stress or strain on the sensor and should be heat treated or annealed. Your as found and your mid are like or greater apart, you probably should run that through an Anneal. Okay. Large shifts can also indicate a seal breach or a leak in the probe handle. That's usually evident when large shifts continue after an Anneal cycle. Okay. Is value on the UUT close to the value indicated on the reference thermometer? If the readout probe has been with coefficients entered in, it will read well within 1 degree Celsius. Okay. Your error should be fairly small. The probe has been changed for one that was bad before, or you don't have any coefficients in there, you could have some extraordinarily large numbers and they may scare you. Just go ahead and continue recording your data, and we'll go ahead and we'll calculate new coefficients and load those in and see how it performs after the new coefficients are in. Okay, so the other thing is spread of the min-max is excessive. Of a standard deviation issue, is your probe plain unstable? Okay, it may be fairly repeatable, but it may not fit the limits of stability. Okay, uniformity rather. Have too large a spread. If you have greater than 2.5 millidegrees of standard deviation, you may also want to anneal your probe just to try to stabilize that down. Okay. So indicate that you may have shortage in your cable. So a couple of good things to watch for. Annealing is put your probe back into an oven or a dry well. Put your max temperature plus 10 degrees for about 2 to 3 hours. Then you let it cool back down, and then you go ahead and start the process all over again. Don't erase your original as found data. You'll just need to take an addition set so that you can get new resistance readings and get a good set of coefficients. All right, perfect alignment. This can be kind of tricky. If you can't do it by hand if you so desire. The equations are out there. It's set up in Excel. You can program that in as well. I prefer to use, for my time and effort, when I'm doing a manual calibration, I use tableware that's provided by Fluke. It does a pretty darn good job of getting the right coefficients and being an accurate system setup. What you want to do when you're using tableware is you'll want to select the PT button, which is the platinum thermometer button, okay, on the tableware, and then enter your probe model and serial information. And then you want to select that sub-range that we talked about earlier, and we're going to have a sub-range 4, sub-range 8, okay, and then once we have selected, we go over to the raw data entry. Okay, and then we always want to go with degrees and with ohms. Okay, very important to do that. If you don't select those, it won't allow you to do any calculations. So I've already put in the 0 value, reference thermometer 0 value, and the distance from the probe system combination. Next, we go to the low range. So put in the liquid engine numbers at -196 and the resistance of the DUT or UUT at 18.3501 ohms. Move to the -38 point. We put that data in there. Then last thing we do is we click over onto the high range tab, and we add the data for the high range. And then we put calculate. Okay. All right. It's easy as that. Here come the coefficients. They're right up there on the screen. You have an option to print them. You can export them as a file to a spot on your disk. You could email them to somebody if they needed them, whatever we needed to do. You can also use exported data. You can put it into Excel and be able to copy and paste it elsewhere. Once we've entered, or once we have those coefficients, we need to enter them into the readout. Okay. So on a 1502A, it's rather easy. You press the button, and you press the probe button, which is the far left button, and you'll see probe on the display. Okay, and then it'll indicate PT or PR90, PR equals T90 rather. Using the ITS90 coefficients. If you happen to have CVD coefficients or ITPS C8, that option is also available. But we stick with ITS90 because they're the most accurate coefficients. Once you've excuse me, words are mixed up this morning. We have the T90 selected. You press enter, and then you R01, the very display, and then it'll flash what the current RTPW value is in the readout. So they use the little green up-down arrows to up and down to change the value of the character, and then left and right to change the position that you're working on. So for this, I would to first character, it would 100. So we leave that at 0, and we select the 9, and continue on through the line. Once we have the RTPW value in, then we hit enter. Okay, and it'll take us to the next coefficient value, which is A, or the high or positive coefficient. Okay, put that value in, and then at the end of each value for the A, B, C, D coefficient that you'll put in, so an exponent rather. And so these should be the neighborhood of -4, 3, depending on type of probe you're using. If you're using a greater industrial probe, it may be as low as -0.2. And anyway, so you put all those in there, and you move on. Once the new coefficients have all been entered, then we start with another measurements. Go through the routine, the as found, the 0 found, our temperatures, our 0 mid, our low temperatures, and our 0 as left. Okay, and you see we've got that all filled out here on the as left portion of the sheet. So we'll logically move on to the next point with evaluating that data. Right. So looking at that data, we're taking the errors that we're seeing from the reference versus UUT or DUT. We're comparing the tolerances that we have here. Now, your tolerances, they generated from what your uncertainty budget is for your process. We go into that in this presentation, but it allows you to add and hard pass fail determination. whether your equipment is operating correctly or not. Okay, so as indicated, I've determined that these all pass and have them set up. It's ready to go. After that, we would generate a calibration report. There are things that need to be included on a report of calibration. First thing would be your lab information, name, address. Calibrating it for somebody that's outside your house. You'll need their customer information, name, address, contact information. You'll UUT information, which is why I make sure that I have that down on my data sheets, so it's always there, present. I can always put it into the report. Okay. You need models, serial numbers primarily. Okay. You need to have a received status and an F status. Reference equipment information. So you'll see in this example report that I have for you, it does have the reference equipment listed. You should have environmental conditions listed on your cert. Depending on what your lab criteria are, it needs to be within spec. I'll need a test date. You make a calibration interval if it's applicable. There are a lot of people out there that when they send their items in for calibration, they request a date of not determined. So we come out, there is no interval date expires. So, and they manage that internally. Okay, unique identifier. That would be your report number. You could use something as simple as the readout number, today's date on it, or actually go through and put your own date code system where you're using alphanumerics to generate a number. So you need to have the relevant data, so as found and as left coefficients, and the data that you had from your the measurements that you took. All right. You want to have your calibration results. That column I had written all the P's in there, so they're all passed. That would be the determination of the calibration results. Okay. Then last of all, you want to have any relevant notes regarding the UUT or DUT equipment. For example, okay, the passed very well, but the sheet on the cable starting to crack and may need to have some maintenance done to it. Whatever you feel. If it's starting to you can say that it is still within spec, but it's like it might be having trouble. Pay attention to it. You can do anything you want to with relevant notes, as long as they're relevant. All right, here's a sample of the report that I wanted to generate for this system. Again, we have the lab information right here. It states that it's a report of calibration. We're going to be having more than one page. We actually have a pagination right there. We have our customer information of a description of what the item is. We have its model. We have its serial. This is for the readout. Okay. Who it's made by. That may not be totally necessary, but it's when it comes to information, sometimes better is or more is better. Okay. And we have our received condition, and our F condition is intolerance. Okay. Then we have a paragraph here, and basically is a paragraph that covers traceability. Okay. It basically goes through and says, yes, this this calibration is good as defined by 17025 by whatever mill standards we might be using. Designates the test equipment down here and the super thermometer with its manufacturer model serial number, the date that calibration expires, the SPRT we're using, it allows these to actually become a transfer standard so that we're transferring the calibration from our calibrations, or from our test equipment, to the actual probe and system. Down here, we've got our environmental condition statements, and then we have a space for signatories. Signatories, they're important. They validate data that's on that cert. Okay, you can do multiple forms of this. You could do, once you're set up for this, you could do an auto sig, which somebody takes responsibility, but the thing is you want to have a very robust process to where you know something can't come through that's a false pass. It needs to be an actual definite pass to have the eligibility for auto sig. Otherwise, you have your calibrations technician. He signs it first, and that says the calibration is good from what he did. And we have somebody that comes through, signs it again, and as a double check, a second set of eyes, make sure the data is correct, make sure all the information up here is correct, because about the accuracy of the cert. This is the product that you're selling. Okay, you don't want to give somebody a bad product. Right. So this report is data. Okay, we have got that listed on the first page. We have our probe page as well. Okay, we got our 1502A on our data. We have our 5615 6-inch probe here, model serial number. We have our reference readout and our reference probe. That's a little overkill, but on the first page, we really don't need the refs equipment on the second page, but we've done it just for illustration purposes. Okay, this left data, or as found data rather, we have all of our RTBW and coefficient information. We have our nominal temperatures. We have our actual temperatures that were taken from the readout. We have actual temperatures from our test equipment. We have their tolerance. We have our pass-fail. And the one thing I didn't talk about earlier is we really state the uncertainties related to our reference equipment. We have that right there on the end. So you know that by how measuring, we have a minus 10 millikelvin uncertainty at minus 200. We have a 5 or an 8 at 8 millikelvin or milli uncertainty at minus 38. We have a 5 millikelvin or millidegree uncertainty at 0 degrees. And then we have 9 and 30, or no, what is that, 10? Sorry, 10 at 300 degrees. Really small on the screen in front of me. I'm trying to solve. So we have good information for the as found data, and we have it looks one failed point here on that column. I can't tell if they're all passed except for the one or not. But I know all the ones on the as left data are passed because we verified that earlier. Notice the rest temperatures or the nominal temperatures on the as found are the same as the nominal temperatures on the as left. And you want to make sure that that's consistent. It adds credibility to your reports. and then our as left data for the reference and for the UUT, our errors, the tolerances, pass fail, the whole all there. So that is a very good product to sell. If you're doing it inside, it also just boosts the integrity of your lab. So, all right. In summary, oh, we went too far here. And, we have two types of system calibrations. We have the verification that we really just lightly touched on at first, and we went through in depth on the true system calibration. Went through guidelines for choosing reference equipment, through system calibration process apps, and that pretty wraps it up. Back over to Steve.
Okay, Roger. We're ready to take questions. Let's go back to this previous slide. Received a few. If you have additional questions, please text those in now, and we'll start answering those. So, Roger, take our first question. Okay. All
right.
This question is, how to determine whether to perform a system calibration versus a true system calibration? Is it strictly per the customer request, or are there other factors to help determine that?
If looking for specifically whether doing a verification calibration or a loop or true calibration, a lot of it depends on the requirements of the customer. It's a request thing. We have two different order numbers, one for the verification and one for the true cal. Also a price difference. When we do a verification calibration, we have 2 points with the calibration itself, and then you can request additional points. So they're at an additional charge. So depending on the number of points that are requested, it could actually be cost prohibitive to do a true or to do a verification calibration where you can accomplish essentially the same thing with a true cal or loop cal.
Okay. This has to do with the calibration certificate that you went through at the end. Maybe you could review about how you indicate the error of each coefficient and the degree of adjustment done on that calibration certificate.
Okay. Basically, you're not looking at a difference in error coefficients. The coefficients are what they are. They're used to the temperature that's displayed on the readout. The coefficients aren't really having an error. What thing is you're displaying the errors of the E versus the readout right. Okay. The difference in or an error in coefficients itself. If you're referring to talking about the readout being compensated for in generating coefficients, why you would have a system calibration and a true system calibration is takes that error, if there is any error, it's just the characteristics of the readout as it is currently set up, because readouts will have a set of calibration constants that are strictly on resistance and eroded or aligned when they're calibrated initially. So if those change, or if the readout itself, if the resistors within the readout drift a little bit, it change, but those should be compensated for by generating new coefficients. So I hope that answered the question.
Okay, the next is, can you run how you would terminals of a 5626 100 PRT to a black stack module?
Okay, for 5626 going to a black stack module, if you're looking at a 2560, that comes standard with the DWF connectors, which are the little push button springs. You'll want to go the red panels will have the red and green, and I believe it's the red and the green, and the black and the white on the black terminals. You can just air wire for those in the push button connectors. There's also a hole that you could use banana jacks. You can spades on them, but I believe it is red, green, and white and black. If wrong with that, if you get a negative engine to begin with, and it's a positive temperature reading, it will be white and green and black and red.
Okay, let's go to the next question. Would like to have some more information about how to calculate the combined accuracy of a system calibration. Are there any good systems that you could recommend for this?
I'm not sure whether we got anything publicized for this. It's based on uncertainty of the reference equipment that you're using, based on the lab environment, based on the heat used, and also it includes the DUT instruments themselves. If I don't have all that stuff that I could actually walk you through that right now, I could probably link into somewhere where you can get that information. Probably through our tech support would be a good avenue.
Mm-hmm. A couple I was going to suggest, Roger. We mentioned earlier in the webinar that we do have that one guide that talks about, say, Fluke readouts and probes. It'll tell you that accuracy. Now, going beyond that, as you mentioned, total uncertainty budget, and we do have a webinar that talks about creating an uncertainty budget. That's it'll be coming again later this year, but we have done that in the past, and it's recorded, and you can reference that on our website. That might be helpful to them as well. I'll move to the next question. The software table for generating coefficients, is it possible to get a copy of it from Fluke? Maybe you could mention more about that software.
Okay, the software that I used, it's actually not so much a spreadsheet, it's an actual program called Tableware, and Fluke does sell it. You contact any of the sales reps, local distributors. They all have access to allowing you to purchase that and be able to use that to generate your coefficients.
Question goes back to system calibration. They're wondering about where and when to do a true system calibration. Is there any additional guidance you can give them?
Really, it's depending on what your needs are. If you have an auditor that comes through, there are some auditors that prefer to have a cal or a loop calibration on your equipment, so they know that probe will not be used with any other readout. And there are others who prefer that you have a calibration for each piece of equipment and then a calibration certificate that says yes, they work well together. It's other than that, it's dependent on what your needs are. If all you need is accuracy, and you don't want to spend a lot of money, probably verification is least expensive. You would have to pay for a read cal a probe cal, and then a 2-point variation cal. And again, if you need points, it would be an additional fee for each point. You could get the going rate right now for a true system cal is $1,310. If you're looking at a system cal, I believe it's $350 for a real now. I believe it's $600 for a pro cal, and then it was $765 for a verification of 2 points. So it may not be a whole lot of difference, but I believe still is slightly less than on a verification cal than it is on a true system cal. So it may be economics, but it boils down to basically what you need is. If your requirements are such that you need to have several points documented, the true cal would probably be the better option in the first place.
Let's go to this question, Roger. Could you explain the process of annealing, including incidental versus intentional?
Incidental annealing would be more along the lines if your probe or your is not exactly stable at, say, a higher temperature. In this case, it would be 300 degrees. If the longer you let it sit in a high temperature, the more likely it is to shift. Okay, so the ideal situation is you want to put your probes and your reference instrument into your bath. You want to wait for approximately 20 minutes to 30 minutes for it to equilibrate, and then as long as it's good, as long as your standard deviation is good, I'd say the reference should probably be less than 1 millidegree. If your reference is good, take your data, record it, and then move on. If you happen to have in and you have an emergency and have to go somewhere, it's better to pull them out and then over when you come back than in the bath. If you're gone for an hour or so, you could have had some incidental annealing. Difference in incidental versus intentional or deliberate annealing is seeing a high standard deviation on your UUT or your DUT in the order of greater than 3 milli milledegrees, of deviation. It indicates that you either had some strain on your sensor or something along those lines. Try to put that into the annealing furnace so that it will release that strain. And to a lesser extent, possibly burn off oxidation. By doing an intentional anneal, by having it at 10 degrees over your typical max temperature for about 3 hours, that should eliminate the unless there is an actual definite problem with the probe.
Are there temperature sources that go to cryogenic temperatures?
We've got the 9190, which is a cryogenic dry well. It did a job. It goes to -90, and it's fairly stable. Apart from that, the coldest temperature that we get in our standard dry wells or metrology wells is -38 degrees. Okay, and that's a stretch. Most of them go right to -38 or 5 rather. but you can stretch them to a point. The issue with stretching them beyond their ats that are into them, they have a shorter life in their block, and you may need to replace them or read them sooner.
Sixth question. Can you use as-found resistance measurements for as left and generate new coefficients for mapping the temperatures?
For as there are two separate things. When you're using the as-found resistance, you're using the as-found reference temperature and the as-found DUT, UUT resistance to generate coefficients. You can't use the same resistance measurements for your left, and you can't use your as-left resistance measurements to generate coefficient as-found temperatures. You have to keep those separate. That's what the calibration is you're taking your as-found data, calculating the coefficients, and then taking as left.
Roger, the as-found data is within tolerance. Will you still recalculate new coefficients?
Yes, we will still do that, even if they're in tolerance. That we don't is if they are less than our stated uncertainties for our reference equipment. If the error is that small, then there's no needed at that point.
Okay. Next is when you're using a dry well as source and monitoring with an SPRT, where the SPRT is the reference, wouldn't the dry well also be listed as a standard on the certificate, since there are some uncertainties still contributed from the dry well?
They would be part of the tolerance group, any heat source would be, but they're not listed as you're doing a comparison calibration using the it's the same as if you're using a bath. Okay, we don't put all the baths that we use on the calibration cert because we're not trying to transfer a calibration from a bath to your equipment. That's heat source only, and we're transferring the calibration from the reference probe to your system. That's the way that would work. There's no need to put a heat source unless you're using the display from the heat source as your reference, and then it defeats what we're doing using a reference thermometer.
The next question is, can you explain metal traceability for a temperature parameter?
Exactly, it's to me like it's meteorological traceability. So I'm thinking it's a typo, but medically speaking, traceability is tracked from a reference standard, a known significant intrinsic standard, transferred to, for example, an intrinsic standard such as a fixed point cell, which all of our reference SPRTs are met with a full set of fixed point cells. Okay, that intrinsic measure or intrinsic temperature is transferred by standards to that reference SPRT, and the reference SPRT now carries the backing of intrinsic standards, and then that there is transferred to your DUT or UUT by means of comparison calibration.
Question: any reason why state mill standard 5662A, which has been obsoleted?
Cert that's at the end, it's an old cert. It's an old example. I haven't updated the mill standards on it. It's just what was there from subject matter that I copied over. It's just an example.
Okay, great. Next one. Can we consider the predicted calculated temperature based on the calculated coefficients as the added data?
I'm not sure what you mean by predicted calculated temperature. What you need to do is once you have your new coefficients calculated, then you go ahead and measure your probes again, your probe and your readout as a system again, in order to get the actual as left data. If you're going to do that in a predictive and not take actual as left data, you have a chance of invalidating all the work that you did before.
It goes back to one we talked about previously. So he says, in regards to intentional annealing, our reference probe has a maximum temperature of 660 degrees of annealing temperature and time in our case.
Okay, for reference probe, you'd never anneal the reference probe. That always is separate. The only thing you would anneal would be the UUT, and that would be the only thing you anneal. If your reference probe is in your lab, and you monitor the rate of that probe by taking a triple point calibration set, you should be actually able to watch the trend of your SPRT. It should be fairly constant, unless you have a problem with your probe. If you've dropped it or something along those lines, and it's actually shifted resistance, you shouldn't have any problem with your ref SPRT. What I'm about when you're doing an annealing is strictly the DUT or the UUT. No reference equipment would ever be annealed unless it's time for its own calibration. But that's a whole different story.
Okay, good clarification. The next question, Roger, is a follow-up to the one about use predicted calculated temperature, saying the drive is well-to-well conformancy specs and stability. These being used in our input budget. This wouldn't I will then be a standard also listed?
That would be up to you. If you want to list it, that's okay. But you're still doing a comparing calibration. That I would say that you shouldn't have to, unless you have not taken any uniformity data on your dry well. We do that with our baths. We have the work areas in the bath, and we actually do a full radial and depth uniformity at once a year on our baths 300 degrees or greater, every 2 years on our baths that are less than 300 degrees. I suggest if you didn't want to put that in your cert, you would have to do a radial and vertical uniformity on the wet or dry well. You wouldn't have to put it on there. If you're not doing that currently, then you probably should list that as your heat source. But I really don't know that it's going to make a lot of difference because you're doing a comparison calibration.
Roger, a couple others that came into your chat window. Let's take those questions. This one is ambient temperature ideal when performing a true system calibration.
All right. Lab conditions, we operate at 23 plus or minus 2 degrees. So we can go as low as 21 degrees or as high as 25 degrees. If we go above that or below that, then we're out of spec in our lab. I would say 3 plus or minus 2 would be the ideal.
Next question is, would it be have a higher accuracy standard in-house to perform a calibration verification of our Fluke DIC 1552A before using standard for calibrating equipment?
Yeah, it actually would be wiser to have a higher accuracy and something that has better uncertainties. To calibrate a Fluke 1552, I also do a lot of those calibrations here in our lab, and we actually use a 1595A and a 5699 to calibrate the stick thermometers as well. You probably could do that with a black stack, and a 5628 would probably be very close. Not quite good as a super thermometer and an SBRT, but it should be sufficient to do that.